The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we'll finish up the Computational Illumination that I couldn't finish last time, and then we'll talk about light fields. We'll talk about assignment number 2, which is on optics. We have 2 options. Some other announcements. Make sure you're checking the wiki and the reading material. There's a lot of material we will not be covering in detail. For example, how a camera works and depth of field and apertures and so on. There are plenty of information online. This particular tutor on YouTube seems to be pretty reasonable. The guy looks kind of scary and has a very shady lighting, but other than that, he seems to be doing a good job of explaining, depth of field. And this particular one is about different SLR concepts. I don't know why he has a pink curtain behind him. Very strange. But he does a very good job, understanding all these things. This URL is up there. Good. So there are lots of ideas for final projects. I would like you to start thinking about them. Just come and join us on this side, as close to this corner as possible. There are lots of ideas. Just come and talk to me, and we have several mentors listed for the class. Professor Mukaigawa is there. He's one of the world's leaders in computer vision, so you can talk to him about your ideas. Or Ankit Mohan, who presented last week, is also a mentor. So there are a lot of people who you can talk to. We also have Matthias here, and you can brainstorm some ideas with him about sensors and so on. And just wanted to give you an update. So these are some of the class projects from last year. So as I said, Schlieren photography was the best project award. The bidirectional screen got the Student Research Prize at SIGGRAPH. And we just heard last week that the Looking Around the Corner project won the MAR prize, which is the top prize in computer vision. So it's extremely prestigious. And Kirmani, who was working on this project, received the number 2 prize. They give out 2 prizes, Best Paper Award and Second Best Paper Award, and he won that. So hopefully your project will also be in that with that level of fame and fortune. All right. So homeworks. There are 3 things you need to do, and I don't think it was very clear to everybody in the first assignment. You need to create your own website where all the information is kept. You need to submit the link on the Stellar, and then you need to submit the input and output photos on the Flickr group for the class. Right now, I think I have only about 6 people on the Flickr group. That means not everybody was able to post their pictures on the Flickr group. And the reason why we have it on Flickr group is that we can comment on each other's results and so on. Of course, the rest of the world can as well, but we can. And hopefully, as we go along in your assignments, you'll be able to create pictures that are not just visually interesting because the guy spent a lot of time with a lot of patience with very expensive gear, but because they're really beautiful computational techniques, and you'll be creating magical photos. Last time we were talking about, there was a fascination with high dynamic range. Right now there's fascination with the tilt shift, but hopefully the next fascination that you'll see on Flickr will originate from some technique that you invent in this class. Maybe a light field picture could be the next one, which is the assignment for us this week. So there are 2 assignments, 2 choices. Sorry for the second assignment. The first one is extending Andrew Adams, who's a PhD student at Stanford. You'll hear his name all the time. He's just done wonderful, wonderful work. And you'll be extending his so-called virtual optical bench. So the way it works is you go to his virtual optical bench, which is built in Flash, but you can use anything you want. You can use Java, C++, MATLAB, anything you like. and it allows you to do operations on light as if you're on a vertical bench, optical bench. So you can put things here. So you can put lenses. And then you can put mirrors, and you can put blockers. You can put, I believe, diffusers, and so on. So you can put any of these elements, and of course rotate them and so on, to create a really useful set of tools to understand how light propagates. So if you're if you're building a HCI system, rather than having to draw everything in Illustrator or on a piece of paper, you can just fire up this application and you can design your whole thing and also understand how light behaves, insert the focal length and so on, and you can very nicely build this your optical setup. So what Andrew has done, and he's graciously offered his source code with us, is he's provided some basic functionality of inserting lenses and mirrors and blockers and diffusers, but it's not complete. So for example, if I change the focal length, so let's see our optics 101 here. So as you can see, this is our classic optics. If I put a lens here, then all the rays come into sharp focus. As I move the lens to the left, the focus point also starts moving. At some point, the rays start diverging. And at what point will they become parallel? If I keep moving the lens to the left. At the focal length, right? So if I move the lens all the way to the focal length of the same lens, then all the rays coming from that will become parallel. And even if I add a second one here, then all those rays will become parallel. Right? And as I bring it even closer, they'll start diverging. And you can use this to demonstrate how to build a telescope or a microscope by adding a second lens and so on. So as you can see, you can play with multiple lenses and things and so on. So it will be a lot of fun. So what you have to do for the assignment is add more elements such as prisms and gratings and so on. And right now he's just creating, just shooting rays, but he's not forming an image. If you go to optical bench, you'll be able to actually form an image. So you have to write a very simple routine to integrate the light from multiple rays and actually form an image, which is relatively straightforward because if I put a sensor here, all I have to do is go to this pixel and sum up all the rays that reach that point, and that's the intensity of that pixel. And as I move this around, the same pixel has no rays arriving there, so the intensity is 0, and so on. And if I add some other point here, then this should add up to become a blue pixel. This should add up to become a purple pixel, and so on. So it's a relatively simple operation, and maybe you have a window here that shows the formed image. And also, it doesn't have an ability to actually enter the specific numbers. So if I want to say the focal length should be 30 millimeters, it doesn't have a way to do that. It's all based on GUI. So there are few minor additions you have to make, and it's kind of an open-ended assignment. The more you add, the better. I'll give you some suggestions on how you can improve it. So that's option 1, and this requires programming, sufficient programming. Option 2 is synthetic aperture photography. So we saw this in the very first class, where you have an array of cameras and you can see behind an occluder. So if I, with an array of cameras, if you're seeing through these trees, by doing some software operations on a set of images, you can actually see around, see through the foliage and any leaves and so on. Okay. So this is what you'll be doing for your assignment. Now, of course, you don't have this $1 million camera array, so we have to come up with a shortcut. And the way we will do that is we will just translate a camera and take multiple pictures. So instead of having a camera array, you can just take your SLR or a webcam, whatever camera you have, even your cell phone camera, just translate it and take maybe about 30 pictures or 40 pictures, and then we're going to do the same operations. And we'll learn about how exactly it's done, how you can see through some occluders. So, you'll be creating this see-through effects by eliminating the foreground pixels. So it's a lot of fun to do this assignment. And there's a third option, which you may want to take, which is saying, so for this one, you actually have to make sure that you're moving the camera in a reasonable way. If you have experience with building Legos, you can just build a Lego robot that moves the camera and takes pictures. Or just manually, you can just mark it on a ruler and just take camera here, take picture, put a camera here, and so on. But all of this involves a little bit physical work. If you want to just stay in your office and look at the screen all night long and do the programming and never have to go and play with real things, you can do the whole thing just in software by again using this virtual optical bench. So you can synthesize the images and maybe in OpenGL or using the virtual optical bench with different viewpoints and add them together and so on. Not as much fun, but maybe you can create even more interesting effects. So it's just an option. I would suggest going with the real thing as opposed to doing it all in software. All right. So let's go back and finish the few topics we left. We couldn't cover because of well, it's coming up. The reason why I wasn't here for the last class was I was at an event called Gadget Off in New York. It's a really great event. If you get the opportunity, it's kind of the gadgets equivalent of TED, and people are blowing up things, crazy displays, crazy robots, crazy cameras. It was a lot of fun. If you go to YouTube and just type Gadget Off, you will see many of the things that well, that's coming up. Let me show you something else. So if you remember, we were talking about Google Earth Live, and imagine if you can fire up Google Earth and you can go to any part of the world and see it live. Because very soon we'll have cameras on every street light, we'll have cameras on every bus, every taxi, and even people carrying their own cell phone cameras will subscribe to some service and they'll be broadcasting, there'll be, we don't know for what, but they will. When that happens, when you can really fire up and go to any part of the world and see it live, it'll be a very different notion than what we think about as mounted cameras. Nowadays we think of them as mostly for surveillance. But over time, they will become, maybe we'll be able to use them for beneficial kind of commercial solutions. So the question is, when is it going to happen? And some of the things are already happening. So this particular project, I'm sure it scares a lot of people that you'll be able to go to any part of the world and see it live. But you can also imagine it will have it will be used for some good reasons. Definitely for commercial reasons. You can have an index of what's people's health in this area. If you just put 2 points and see how long it takes for people to walk across these 2 markers, that tells you how healthy people are in this town, or at least how much in rush they are all the time. If you are a real estate agent, you can figure out what's the property value of this area based on what kind of foot traffic you get at a particular restaurant. If you want to go to a restaurant, you can find out is there a long wait there, and so on. So this was a project at Georgia Tech, Irfan Essel's group. And it's an interesting concept. So remember we had a poll about when do we think a digital camera as a standalone device will disappear, and most people were between 5 to 10 years. There were a couple of people who said even 2 years. I think the mean was somewhere between 5 to 10. So here's another question: when do you think we'll have Google Earth live? When you can fire up and go to any part of the world and see it live. You won't be able to do it in the middle of Iowa.
What percentage of the world are you saying?
Let's say at least one city. That's it.
At least one city?
That you can fire up and go to any one particular city, let's say Manhattan, and see it
one
live.
particular city or any one city or any city?
Any one particular city. Any one city.
One city.
Yeah. It could be Tokyo, it could be New York,
Okay.
it could be Sioux City.
It would probably be London, right?
Oh yeah.
Yeah. But remember, it's not surveillance.
Right.
It's not surveillance. It's a commercial service. The same way people are thinking about creating free Wi-Fi networks.
Can't you do that? This was just on a TV show, but I feel like didn't they have something with webcams, publicly available webcams, like all along the border? So you watch the
Minuteman effort or something.
people running across.
Yeah, I think that's what it was called.
So
isn't it?
I guess that is real.
Right. But again, think away from surveillance. All the efforts we have seen so far are surveillance based. And the video that you just saw is not about surveillance. It's about watching sports games, getting a sense of what the traffic is on the street. So right now all these street level maps and aerial maps are completely lifeless. They're just static snapshots. And you want to add some dynamic element to it. It may not be realistic. Maybe there are technologies that shows a flow of people, but you cannot recognize who's who. Right? So there will be all these other kind of overlays on top of that. So just like when Google Street Maps came around, you could see the people, and now the faces of people are blurred, or the license plate number. But in the beginning, everything will be free for all. Pretty scary, but
It brings up a lot of weird issues of voyeurism.
certainly. I mean, it's the same issue that Google Street Maps. Yeah.
I think we will have Google Earth when they will launch their own satellite.
Which is when
But satellite that's in a geosynchronous satellite, or somewhere that's like a blimp that's floating around.
If media have their own satellites, then they can take their own picture, their own equipment. It's possible or not?
It's too far away.
Really?
I mean, satellite is too far away.
Okay. You have a small satellite. Okay. It's possible.
But you also want to exploit infrastructure set up by somebody else.
Okay.
So you might send your own satellite to look at, your ex-girlfriend, but you want to also exploit existing networks, and maybe you won't have to because there'll be enough cameras. Today Google might come and say, "I'll pay you $5 a month. Just aim the camera outside your office or outside your dorm room or outside your shop, and we'll pay you $5. Just give us the stream." And for me, it doesn't matter to me. I can just aim it outside. But by using that network, they can provide this service.
There's a bus tracking proposal project that did that for people who just set up cameras outside their house.
See? Yeah.
And they were en route.
Yeah.
And use that to figure out where buses were in the city because there wasn't enough money in the city to pay for tracking buses.
See?
I can also imagine getting a camera on every cab or something. In your city. And
exactly.
It's like you're having a fleet of Google Street View trucks
Exactly.
that are all.
And they'll be live because they can figure out the condition of the roads. They can tell you about traffic. They can tell you about potholes. They can tell you about rain or no rain.
Yeah.
In fact, there was a very nice project in Tokyo where they placed just on-off detectors, not on-off detectors, but detectors on the wipers of taxis. And from that, they figured out, they got a map of the whole city and how much it's raining in which part of the city. And that was, of course, much more accurate than the weather reports that they were getting because they just measure it in some bucket, how much it's raining. And here, they're not measuring rain, they're just measuring how fast the wipers are moving all over the city. So that's kind of an indirect way of capturing visual data. So one city, how many years it will take? Yeah, we'll do a quick poll. You have to put your vote on the line.
I'd say 2.
2 years?
Yeah.
Okay.
Either be a European city.
Very 2 years last time as well?
Yeah.
All right. So you're a 2-year guy. All right. 10 years?
Yeah. One city.
Just one city, yeah.
One city.
Yeah.
So which city? Las Vegas?
Probably some city that wants to.
No, Vegas doesn't want to be that.
It has to be a city where something interesting is happening. So I'm guessing it's not in the U.S. first of all, because there are too many privacy issues.
Yeah.
It's going to be.
It would be like a Hollywood, but maybe in another country. The equivalent of.
Yeah. I can imagine a city like Hong Kong or something.
Yeah.
Singapore would do it.
Yeah. Singapore.
Singapore also. Yeah. All right. Yeah. Any city in the world. So 10 years. We should go the other way. 5 years. Sorry. Wow. 10 years. And never. Wow, JB. Only satellites, right?
Yeah.
Not. Okay, don't cross your path with JB because he'll put his satellite, on your trail.
$8,000, right?
What?
It costs $8,000 to put in.
It's very cheap to small satellite. And you can shoot it like a bullet.
But the imaging is not that easy.
It's not easy.
How are you going to image from 3,600 kilometers?
Yeah, that's the problem.
Yeah.
Yeah.
A lot of software.
Oh, yeah, just zoom. Yeah. In software. Right?
It will also need a lot of data storage. I mean, you can store the whole world's history.
Right.
Based on this Google Earth, like if you have the records and archives of this, and you can actually track back all the crime scenes, it's right possible. You need a super huge data storage for that, because like storing complete world's live history is difficult. So it depends what's important and what you really want to store.
Store it all in memory.
Certainly. I mean, storage, EMC will be happy if you come up with ideas where, you have to store more and more. I remember when, back in the days when Mosaic was around, in the 92, I remember if I open the Mosaic homepage, they listed every website in the world. Do you remember this, Matthias? Right? And over time, of course, there's no way you can make a list because everything is so dynamic. You still have places like archive.org, I believe, where you can time shift and look at how a web page looked over the last 10 years or so. I don't know how far back they go. But you can go to my homepage, for example, and you can see how it looked every few days over the last 10 years.
Though, like you have to be a certain popularity to make it there.
I'm sure, yeah. But still, the fact that they're keeping a snapshot of the whole World Wide Web over time, and over time will make a record of the whole world visually, not just of the websites. So it's going to happen.
I went to a conference in 2000 and somebody came with a book. And it was internet. It was all the URL on the book.
Yeah, everything printed.
Yeah, that's what it would be like, like we have for telephone. You could record.
Right.
Yeah, imagine if the telephone book. Imagine if it was the equivalent of the internet book every year. You got this bigger and bigger yellow book.
Yeah.
Awful.
So the complexity of data and bandwidth and computing and memory just grows exponentially. I remember when I was in grad school, the hot topic was how to assign IP addresses for mobile devices, like mobile laptops. That was like a huge research problem. And now, we are flipping through it, all the time, completely seamlessly. So we don't even think about that as a problem. So it's a similar situation here in the visual domain. Remember, this is going to be the decade for visual computing. But we're not just talking about social implications or business opportunities in this class. We really want to think about what kind of cameras make sense. If you're going to put a camera on every street light or on every taxi cab, what kind of camera should be developed so that it's compatible? If you put a camera on a taxi cab and you keep taking photos, it's all going to be blurred. It's going to be totally useless. If you put a camera on a street light, it will be wider field of view, but you will not be able to see anything specific. There are all these issues that come up. maybe you should exploit different wavelengths. You should use different optics, different processing. Maybe they should talk to each other and do some coordination, and so on. So these are some really interesting challenges. So could be one of your final projects. I think they're finally up here. So last time we were talking about computational illumination, and we saw several examples like creating cartoons directly for HCI, or doing flash matting by taking pictures in the foreground and background. And we'll cover just a few more projects before we switch over to optics and light fields. So here was a recent SIGGRAPH paper where if you wanted to create an image that's more comprehensible, like on a leaf, where if you take any one of the photos, it may not show the structure very well. You can just put an object, keep the camera fixed, put it in a video mode, and just move the flashlight around, just randomly. And you collect a set of photos, maybe 3, 4, 5, 10, and then you do some computation on that to create an image where you can enhance the shape, or you can, so here you're enhancing the shape, here enhancing the detail, and so on. So, there are lots of techniques that they showed. For example, there are 5 input images. Yes?
What do you mean by the shape and superficiality here there? What's the difference?
So, in case of the leaf, you want to show the relief. How are the folds?
I mean, the overall shape versus the sort of texture shape.
The terrain.
Right.
That's what I mean by shape. Not just the outline. But for example, here, it's the shadows. I mean, it's illuminated as if the light is at a very grazing angle. So the relief or the terrain is more clearly visible here. Right? So you can see the shadows here and so on. So we know that this particular structure is much higher than this particular area, and so on. So the height field of that is enhanced. On the other hand, this one shows all the texture in great detail, but it looks like a very flat leaf. So you can have knobs in your software which says, show me more of the detail or show me more of the shape. And you can trade off between that. And they came up with multiple methods. This particular method, again, put this 3D object, move it around, and create this particular result. This is my older method, the one I showed for doing the day and night images. So they compared with that, and their claim is that if they use my method, the shadows are preserved, which is true. And in their methods, they can create, more beautiful combinations by using multi-scale decomposition of bilateral filter. And we'll talk about that at some other point. So this is very unique. As a photographer, you would never think of setting up the lights in such a way so that in post-capture, you can decide whether you want to highlight the shape or the detail. Okay, so that was so far light position we were changing, but there are lots of other parameters we can change for the light. So let's look at this project called Dual Photography, one of my favorite projects. And we also saw it as a teaser, where the experiment they want to do is read this card from this camera, although it's facing away from the camera. Okay. So what they're going to do is place a projector in the line of sight and some kind of a reflective surface. If you shine light from this projector on just one spot, okay, it's going to bounce around on the book and eventually arrive at the camera. Okay, and by shining one light at a time, this is what the camera will see directly. So again, this card is facing away from the camera. You're going to shine different pixels on this card, and you do this 1,000,000 times because you have 1,000,000 pixels in the projector. So after taking 1,000,000 photos, this is what you'll be able to see from the camera. So this is a dual photo.
What does one photo look like?
One photo looks like this.
Oh, okay, so that's it.
Yeah. Any one of all the photos look almost like this, except when you shine the red part of the card here, this book will look a little bit reddish because it will be cast. And if you shine the yellowish part, when the projector shines the yellowish part on the card, there'll be a yellowish glow. That's it. And from that, you can figure out how this works.
It still requires line of sight.
Sorry?
It still requires line of sight of the object, right?
The projector has to be line of sight.
So you had to put something in line of sight.
Yeah, but it's cute. I agree. It may or may not be practical, but it's very interesting. There was a very a project that received a lot of press about 5 years ago, where some guy came up with a technique to figure out what you're reading on your monitor by just looking at the window. So imagine it's a nighttime scene, and you are in the room working on your monitor, and if you stand outside, somebody stands outside the window, they can see the glow from your monitor in the room. Now the question is, can they figure out what's on the monitor by just looking at the glow in the room?
Yes.
How?
Because they can synchronize with the scan of the monitor.
Exactly. So it won't work for LCD, but if it's a CRT monitor, only one pixel is being illuminated at a time. So if you have a photo detector that's aimed at the window and it's running at the speed of the CRT, and you synchronize it, you'll be able to actually read what's on the CRT monitor. So for TVs, at least old TVs, it's running only at about 30 hertz or 60 hertz. So it's really easy to figure out what's, if the image is sufficiently high contrast, you can figure out what was on the TV or the monitor.
This is how they track the TV license in the UK. There's this thing called Tempest. You know Tempest effect?
No.
So if not the light, but the electromagnetic radiation of every component on your screen is tracked by an antenna, then you can deduce what is the activity of the device. It's valid for every device that emits any radiation. So they have this truck, they go in the street of London, and they aim at every house and they see which channel they are looking at and they pay their TV license. So you have extended spectrum of analysis Tempest.
Yeah, but they're looking at RF. They're not looking at visual spectrum, right?
RF.
Yeah, RF spectrum.
Yeah, and actually a while ago there was Tempest-proof fonts that were supposedly able to mask your online activities from Tempest spying.
Yes.
Yeah, I don't know how good those work though. There's new methods also to directly read memory off of people's computers, so you don't even need to think about what they might be running. You just go, oh, that guy's.
You mean disk memory or
no,
RAM?
RAM. Wireless.
Based on the
Based
on electromagnetic.
Yeah.
So there's a lot more coming.
Yeah.
Those at Google Earth Live, you're worried about only what's in the line of sight. There's much more. All right. So how does this work? So again, you have a camera, you have a projector. You're going to take this is how the camera looks at it, and this is how the projector looks at it. But eventually, you'll be able to compute an image that looks like the one on the right. Okay, and all the caustic and shadows and refraction and reflections are all captured there as well. All right. So I'm going to go through very quickly because we covered it. But here's the point: that you're going to turn on one point, and some light will reach the eye, and that's just a regular photo in the primal domain. Now, if you replace the light and eye, and this is the Helmholtz reciprocity for in the optical domain, if you replace the two and shine the same spot that the eye was looking at, you will receive the same exact intensity. Okay, and it takes into consideration the bidirectional reflection distribution function, the R-square fall off, and all those things. So this duality is extremely powerful, and it can be exploited in many ways. So this is how a barcode scanner works. You have, when you go to the aisle, you have a scanner that's just scanning a laser stripe across the barcode, and there's just a single photo detector. As you, if you hit a white spot on the barcode, light gets dispersed and you can detect it. If it hits a black spot, then you don't see it. Now, instead of using a photosensor, let me go back. So this way, by scanning light and using a photodetector, what we have created is basically a situation where you have a camera and a omnidirectional light source, like a bulb. Okay? So in case of barcode scanner, it's as if the barcode was lit by just a flashlight and you took a picture with a camera. Except the barcode scanner in checkout aisles does not have any camera inside. Okay, it just has a laser scanner and a photodetector. So that's the simplest version of dual photography, that you can record light by the so-called flying spot principle. You illuminate the spot and you see how much light was reflected from it in aggregate. Okay, so that's the basic reciprocity. Now, okay, so let's look at the math for this very briefly. Okay, and it's very straightforward. So just follow me one step at a time. So let's say I turn on the first pixel of the projector and record the intensity of light. Everybody's trying to remind me of intensity. I record the intensity for first pixel. Then I turn on the second pixel, I record the intensity. Third pixel, and so on. Okay. Now, if you replace the photosensor with a bulb and the projector with a camera, the claim is that you will receive the same exact intensities. Right? So with a light, I'm going to just floodlit the scene directly, and the claim is that the first pixel will receive the same light that the photodetector would have received over here. Okay? And so on. Is that clear?
But isn't, for example, the first pixel getting reflections from all over the rabbit?
Mm-hmm. Yeah. That's the point, that it will reflect all over the place. But if you look at that point directly, because of the duality of light, you can replace your eye and the light source, and you will see the same exact intensity in that particular direction. In case of the analogy I gave you of being able to see what's on your monitor by looking at a window, you just the light from your monitor lights up the whole room, and some of the light leaks through the window, right? But it doesn't really matter. There's some proportion of light that leaks through the window, and when the next pixel turns on, the same proportion of that light leaks through the window.
Yeah, but I get that because every pixel is being turned on and off in an order.
Right.
But here, all the pixels are being illuminated at the same time.
No, in the experiment, only one pixel is being turned on at a time.
But then the light bulb is it's also flickering the same way the projector is doing?
No, it's not. It's not. That's a good point. So here you understand that only one of them is turned on at a time, and we are recording it on the photodetector. Now, when you have the light source, the point you're making is that light will reflect, light will come in from here, it will bounce from here, and it will reach here. But light could also bounce from somewhere else and go in the same direction. It will not, because when you shoot a ray from this projector, it will hit only one point.
Okay.
And that particular point is lit by this light in only one direction. So there is still this 1:1 mapping between the two.
But you have light that bounces it bounces, hits some spot, hits a mirror, lands on that spot again.
That's a very good question. So when you have interreflections, we'll see that in the second half, how we deal with it. So this is a very simple demonstration where we have only 1-to-1 correspondence between the direction of the light and the direction of the pixel.
So you could do a camera just with the projector and the arm, and the light sensor?
Yes, basically.
Because if you have prior knowledge of the scene that you're imaging, you can dramatically reduce the number of
Measurements.
Like for that card example, you didn't actually need to do 1 million to figure out what card it is. You could probably do it with a few hundred.
How would you do it?
Figure out where the symbol is first. Find the corner by.
So you're saying that
figure out
you're saying the white part of the card, I don't need to illuminate that at all because I know it's already white. Is that what?
Sorry?
The white part of the card, playing card. You're saying I don't need to shine those parts because there is no information there. Is that what you're saying?
And then you don't have to shoot the whole card all the time. You can just shoot the little tiny corner where the K or the Q or the 7 is, and that's all you need.
But then you'll capture only the K. You will not capture the rest of the card.
Well, that's all you need.
Yeah, but to get a card.
Okay, all right. Okay, now you're thinking about actually playing bridge or something.
Yeah.
The relevant information is.
Yeah, could be. But you don't know where it is, right?
Well, if you use the projector to first scan one horizontal and one vertical, you get enough information to figure out where the
There's some
information is.
Certainly, you can come up with some optimizations. If you really want to, you really want to read opponent's cards, if that's all you want to do, I'm sure you can come up with interesting things.
But I mean, for other applications where you know what you're looking at, but you're looking for some very specific thing.
So you could do some binary search.
Right.
So, for example, when JB asked, can I just use a projector and a photosensor to look at something? If all I want to do is locate some retroreflective dot, then yes, you might be able to just shine a whole vertical line, sweep across, and then another line and sweep across, and that will quickly give you the X and Y coordinate of that spot. Right? So yeah, you could come up with quick simplifications. All right, but this is standard technique that we have seen many times. We're going to go beyond that now. But is this part clear now? That we're going to measure the intensities and they'll be the same in both directions. Okay, now we're going to go a little bit further. All right, so this is what they get. These are the kind of images they get by using this mechanism. All right, not great quality, but reasonable. There's a bunny there. All right, and flying spot camera. That's exactly how it works. You have a spot that's moving around, and that's how scanning electron microscopes work. It's not a high quality camera, but a high quality light source that's very focused. So you have a sample, but you illuminate the sample at only one location, and then you have a detector that integrates light over the whole sample, and so you can do a very good job of that. Now, instead of a photosensor, we're going to make it a little bit more complicated and replace that with a camera. Okay, so what we're going to see throughout this class today is how we can start thinking in higher dimensions and realizing that the appearance of the world is not just flat 2D, but actually it's much higher dimensional. In this particular case, how many dimensions do we have? When we had a photodetector, the photodetector is 0-dimensional and the projector is 2-dimensional. So the measurement was 2-dimensional and we got an image out. How many dimensions do we have here? 4. We have 2 for the projector, XY of the frame buffer of the projector, and 2 for the camera, the UV. Sorry? There's time dimension as well, but right now everything is static and things are not changing over time. You could say there is wavelength and so on, but we are ignoring that as well. We're just assuming it's just grayscale. Okay? So now we're going to think in 4 dimensions. All right? So now what we're going to do is exactly the same thing. We're going to turn on, we're going to assign some coordinate system, PQ for projector and M for camera. And we will realize that just the same way we swapped the eye and the light source, we'll be able to swap the camera and the projector. Okay. Now coming back to primal, same trick. We're going to turn on one particular pixel and of the projector and read one particular pixel of the camera. Except, because it's a camera, I can read all the ML pixels simultaneously in one snapshot. I don't have to read them one at a time. But the projector, I can only turn on one PQ pixel at a time. Alright? So that's a 4D mapping. I have 4 functions, 4 parameters, PQ, MM. And for every PQ, MM, I have one value. It's a function of 4 variables. Alright? And then to capture that, it's a little straightforward. Right? I'm going to turn on 1 pixel of the time of the projector. And I'm going to record 1 image, M times N. Okay? And this is a very standard method in linear algebra, where instead of representing it as a 2D, you represent it as a single vector. So let's take some numbers here so it becomes easier to remember. Let's imagine the projector is 1000 pixels by 1000 pixels. Okay, and the camera is again, so let's say it's 2,000 pixels by 2,000 pixels. Okay, so this particular vector is now going to be 1,000 times 1,000 times 1. So you'll have 1 million entries corresponding to each pixel of the projector. Okay. The image that you get is now 2,000 by 2,000. So it's 4 million. There are 4 million entries in this particular vector. Okay, good so far? Now we're going to come up with a relationship that maps these values to these values. Because remember, when I turned on one pixel here, it made contributions to all these 4 million pixels out here. And we're going to try and represent that mathematically. And it's relatively straightforward. We'll just go slow, one at a time. Okay? And that transformation we're going to specify as this matrix T, which is now, what's the dimensionality here? M times N is 4 million, and P times Q is 1 million. Okay, this is a huge matrix. 4 million by 1 million. Okay, so this is, in already in terabytes, sorry, gigabytes, 10 to the 12. So 4 terabytes, right? All right. Now, this is how we're going to build this matrix. We're going to fill up the values in this matrix. Remember, every time I turn on a projector pixel, I get 4 million values. Next time I turn on projector pixel, I get 4 million values in the camera. Okay? So 1 million times 4 million is what we're going to do. So very simple. I'm going to turn on the first pixel of the projector and see what image I get. Okay? And that value will go here. Alright? So the 4 million values will simply go here. And that is the image I'll be captured. So again, turn on the first pixel of the projector, see what image I get, which will be this 4 million values, and those values are simply the first column of this transform projector. Okay. Then I turn on the next pixel of the projector, record the image in the camera, and that becomes the second column of this transformation matrix, and so on. Okay. Now, it's very easy to see what's going on here. If I turn on both pixels, the first pixel as well as the second pixel, what image should I get?
Sum of both the columns.
The sum of the first two images I got. So again, if I turn on the first pixel, I took a photo. I turn on the second pixel, I got the second photo. If I turn on both pixels at the same time, I'll simply get the sum of those two photos. And that's what is being represented here mathematically. So if I put a 1 here and a 1 here, then the matrix multiplication will say these two values multiplied by 1 and 1 here, the sum of that goes in the first value. And again, the same two values in second row, not same two values, different two values in this row multiplied by again the 1 and 1 here, go to the second value here, and so on. Okay. So we're going to set up this huge linear system by just probing the scene one pixel at a time. And so filling up this T matrix is relatively straightforward. I turn on the third pixel, take a photo, and that photo becomes my third column. Okay. Very simple. And you keep doing that, and you can build your T matrix. Again, a lot of data, but that's research. All right. Now, if you had let's say you had this wall or simple screen, and I put a projector and a camera, what will happen? If I turn on one pixel of the projector, how many pixels of the camera will get a non-zero value? Only one. If I turn on the next pixel of the projector, some other pixel of the camera will get the value, but only one pixel in the whole image will be actually non-zero. Right? So if you have a scene that's relatively simple, maybe just flat or a convex object, in T, every column will have only one value that's non-zero, or maybe a couple of values if the camera has high resolution. So the matrix T will actually look very sparse. Most of the values are 0, only some values almost along the diagonal will have non-zero values. On the other hand, if you have a scene with lots of interreflections, if you're looking at a corner of a room, or there's a glass bottle and all this complexity, when I turn on one pixel of the projector, many pixels in the camera actually get the intensity. The first because of the bottle, the next because of the screen, the third because of interreflections in the screen, and so multiple pixels in the camera will be lit. And so the matrix T will be very dense, because remember, every column there, more than one entry will be non-zero. So that gives us some. If I just look at the matrix T, if someone just shows me the matrix T, the gigabytes or terabytes of data in just a visual representation, I can tell you from what kind of scene it came up, right? So just to make sure it's clear. So it's the projector, it's the camera, it's the transform matrix. If I turn on the first pixel, the photo that appears because of the first pixel, I'm just going to put it here. If the scene was very simple, where I have a projector and a camera, and I turn on one pixel, and it maps to only one camera, then only one of the values will be non-zero. The rest of the values will be all zero. And if I turn on the next pixel of the projector, only one of the camera pixels will be lit, and so on. So maybe I'll have a value here, a value here, a value here, a value here, maybe a value here, and so on. Every column will have only one value that's non-zero. Everything else you should see. And that's a sparse matrix. On the other hand, if I have a scene that has a lot of complexities, there's a glass bottle here, there's an interreflection here, and so on. When I turn on one pixel of the projector, it reflects from here. It reflects on the back of the bottle to some other pixel. It hits this wall and goes to some other pixel. This light reflects off. Reflects other pixel. So maybe 10 or 15 different pixels of the camera will be lit. So in this case, when I write the matrix, for the very first entry, in the first column, multiple values will be non-zero. And when I turn on the second pixel, similarly a lot of values will be non-zero, and so on. So this matrix is actually pretty dense. A lot of values that will be non-zero. So by just looking at this, visually looking at this structure of this matrix, I know how complicated it seems. Okay. This is very useful, and this will keep coming up in as we go along. Is this clear? All right. So this is what we call our primal space, which is turn on one pixel of the projector, take a photo. Now we want to create the dual space, right? That was our dual photography problem. How will the picture look like if I put a camera where the projector is? And we're going to solve that by doing very simple operations on this matrix. Okay. So again, we spent all this time taking 1 million photos but turning on one projector pixel at a time. Now is the time to see the money. Right? This is the problem I want to solve. Okay. If I put a camera where the projector is, how does it look? So I need to come up with a transformation T, a modified transformation that will map my camera pixels to projector pixels. Right now we're mapping projector pixels to camera pixels. Okay. That's the question we have to answer. And let's call it T double prime. And its dimensionality is now, the upper one was 4 million by 1 million. The bottom one is 1 million by 4 million. Okay, that already gives you a cue of what you could do. So if I turn on pixel J of the projector, pixel I of the projector gets certain value. And it corresponds to this column and this row. Now, let's call it pixel that. And now, when I put the camera at the projector, I want to say which pixel of the camera, when I look at a pixel I of a camera, which projector pixels contribute to that. Okay, so I took this 1 million pictures. Only when some of the projector pixels were turned on, I got a non-zero value at this on this camera pixel. and that's also a very similar structure. Okay, so the hint for that is the matrix T double prime is simply a transpose of the matrix T. Okay, you just flip it along its just flip the horizontal and vertical coordinates of the matrix, and that gives you the T double prime. As simple as that. And from that, we can compute an image that appears as if the camera was placed at the projector. So here are some examples. So here's a picture taken by when the projector was floodlit. This is how the camera looks at it. We're going to probe it multiple times and recompute an image as if the camera was placed at the projector. Okay. In this case, it's still all diffuse, only 1:1 mapping. There's no interreflection, there's no glass, and so on. So it's relatively easy to compute. Here are more challenging examples. So, where's the projector in this case? It's a little bit to the left. You can see all the shadows going back, very deep. And now we're going to create from this a photo as if the camera was placed at the projector. Okay. Will we see shadows when we create that picture? What will we see? Okay, you won't see the shadows because now your camera is placed where the projector was. But you'll see something else.
It's like a shadow on the horse.
Sorry?
It's a shadow on the horse.
Exactly. So why do we have shadow on the horse? Because so now, although the horse was lit where the projector was, we swapped the projector with the camera. And from the camera's viewpoint, the horse was actually occluded. So when I swap the two, now I don't see the light on the horse. So it appears as if it's in shadow.
So are those real or are they simulated?
This is real. They've spent days and days capturing this data.
So this is not a shadow, it's an occlusion.
You can think of it as an occlusion. What is occlusion? How do you define occlusion?
We can't see parts of the horse because the color is in
How would you define it more precisely?
Light can't get to it.
No light.
Light cannot reach. So if I shoot a ray, right, we're going to talk about rays a lot in the second half. When you shoot a ray, the ray is occluded and it stops the path of the ray, right? And that's occlusion. So when we think about light, it's very obvious because the ray starts from the light source and it's occluded and there's shadow on the other side. But even for cameras, there's occlusion. If I'm looking at this monitor, I cannot see what's on the other side. So this is like the inverse ray because I'm shooting the rays from my eye. In fact, the Greeks used to think that the way we look at the world is we shoot the rays from the eye, and they were right. Because the duality of light, you can just shoot the rays from your eye, and it's the same math after that.
So is it like in the computer, in the rendering graphics, you have raycasting? That? And the question here is that was there totally dark before the illuminator? Do they have ambient lighting?
No, just certain.
Control everything.
They have to control everything.
So we cannot use this in a room like this with external lighting. It has to be very controlled.
No. I mean, whatever additional term you have, it will remain.
Okay.
Or you can take two photos, one with the light source, one without the light source, and subtract it away. So you can do all those things. But you're right that I cannot do this in broad daylight because the light. It's like taking a flash photo in broad daylight. The flash doesn't make any difference because it cannot override the sunlight or doesn't make significant contribution above the sunlight. It's the same thing here.
So computationally, how easy is it to get that spectral expansions?
I mean, if you have enough memory.
You can do that, but is that how it was?
So it's not that easy to take if you have a small matrix, taking a transpose, is very simple, just n square, right? Just take the value and just change its x and y coordinate. Make x y and make y x. Very simple. Even a million by 1,000 by 1,000 image, 1,000 by 1,000 matrix, no big deal. But eventually you'll run out of memory. If you load the whole matrix and try to invert it, it's going to be a challenge. Just think about taking a sheet of paper, and all I want to do is do its transpose. If the room is limited size, I can take bigger and bigger sheets and do the transpose. At some point, if you give me a really large sheet, I won't be able to do the transpose. Although the task is very easy.
Well, I mean, you don't even need to do that. You just need to do that addition, right?
Sorry?
All you do to make the images, you add up each of the columns. So can't you just?
So you can do it mathematically, but you may not be able to load the whole thing in memory.
But you don't need to. You just access.
Exactly. So you just do this
and then forget about it.
Exactly. So you won't be able to do this. You won't be able to do this in kind of a real-time manner. But if you do some disk access, then you'll be able to do it. And in the paper, they describe all these challenges. And if there's time, I'll just show you very briefly what approximations they came up with that allows them to load this quickly.
Very briefly, does it exist projector and camera in the same package? Then you can switch between shining light through and receive? It's always different in the picture, the projector and the camera.
Right.
But the other that they are friends, they are and you could use it see-through or for receiving things.
Right.
Does it exist in one package? Or
just to clarify, in this particular case, it doesn't matter where the projector is and where the camera is.
Sure.
You can just put them arbitrarily. Of course, they can't be too far away, but as long as one can see the impact of the other. Now, are you saying that they should be optically coaxial?
It could be interesting for research.
Yeah, certainly. I mean, my thesis, by the way, my PhD thesis was projector as a dual of a camera.
And you built one?
I built many versions, but actually in Hiroshi's group, there is a concept called I/O bulb. And
it was a concept of the web, and it was more asking of a physical device.
But I remember John and others actually built kind of projectors and cameras that are coaxial and for interaction and so on. I mean, other people have built it as well, but they show a lot of interaction on top of that. So the concept of putting them together for some specific tasks is well known. But what this group showed was that mathematically, you can create these magical pictures.
Do you get a resolution difference?
Of course. So that's a great point. So you might start with a 10 megapixel camera, but if your projector is only a megapixel, then when your dual image is only going to be a megapixel, and there are going to be a lot of aliasing issues and so on. So that's a very good point. And it will also impact if the projector's color properties are going to impact how you capture the image as well. It's not purely dependent on the camera quality now, camera sensor quality now. It's also dependent on the projector's illumination quality.
Beyond the challenge, how they justify this technique? Is there a scenario of use or application of that?
I didn't hear the last part.
Beyond the technical challenge,
right.
Did the author of this paper have a scenario, say, it could be useful for this? Or
yes, I'll show you. I'll show you their motivation.
Okay.
But as you can imagine, this can be used in many other ways. It's not always practical because you have to take 1 million images, right? But at the same time, I'll show you the reason where it does give a lot of benefit. Any other questions? All right.
You don't always have to take 1 million, but don't they show how to do the
subdivision?
Subdivision.
Yeah, I'll show that very briefly. It's kind of a second order effect, and I don't want to go too much into detail. And now you can do really complicated scenes, such as some global illumination. So the caustics and so on. It's all captured. And then you can start doing some special effects. So remember, the picture on the left was taken by the camera. The picture on the right was computed as if the camera was at the projector. On top of that, now that we have swapped the projector and the camera, I can convert the projector into a slide projector mathematically and see how the image looks. So if you go back to this matrix, I can just put all ones here. That will be a flat field of the projector and see how the image looks. And similarly, I can put all ones here to see what happens when I switch the camera and the projector. But I don't have to put all once. I can put 10, 10, 10, 10, 10. That means as if I put a slide projector where every pixel was on and off. Every alternate pixel was on and off. So you can create slide projectors to create those effects. So you can create interesting effects like this.
But you can't do that backwards on the original.
You can do both ways, of course. I mean, in the primal domain, it's very easy, right? Because I can turn on one pixel of the projector, take a photo. Next pixel I don't turn on. The third pixel I turn on,
So, yeah.
and I can just take addition of those 500,000 photos, and I'll automatically get this effect. So in the primal domain, it's very easy to do.
I think in the primal domain it's even easier. You can just literally project that slide.
Exactly. Exactly. But the point is that if you had collected this terabyte of data, from that you don't have to think in advance which slide you want to project. You can change that slide in software. You understand?
Yeah.
This is the same effect as we saw earlier where the woman was in a dome.
Yeah.
The Milan versus LA. And post capture I can decide how she should look for relighting. Alright. So let me skip over the rest of the slides. It will be available for you and go to the next part of okay. The motivation for them was this, and again thinking in even higher dimensions. So we just realized that the lighting and appearance, I mean lighting is two-dimensional, the photo is two-dimensional, so it's already four-dimensional. But we're going to go now in much higher dimensions. Okay? So instead of putting just one projector, imagine if you started putting multiple projectors. Okay? So instead of turning on one pixel of one projector, of the given projector, now I have 4 million pixels. A million pixels in each of the projectors. So this adds, additional 2 degrees of freedom, because if I have a projector, I can place it anywhere in 2D. So you can just think about the hemisphere, any azimuth and any elevation, I can put this projector. And every projector has a buffer with XY. So the illumination itself now becomes 4-dimensional. 2 degrees of freedom for the position and 2 degrees of freedom for the pixel coordinate. And the camera is still 2-dimensional. So how many dimensions do we have now? Sorry? No? No. We have 2 for position of the projector, 2 for coordinate of the pixel of the projector, and 2 for the camera. It's 6, right? So we're increasing our dimensionality here, and the problem is getting more and more crazy, right? So imagine if you want to do this, how would you do it? It will take 4 million steps. You'll have to take 4 million photos. But there is a shortcut based on what we just saw. How can you reduce the total number of pictures? So this is thinking in primal domain. Duality. How will you exploit that?
If you switch the camera and projectors the other way around.
Exactly. And the benefit. So now if you switch the I think it's on the next slide. So that's 4D, that's 2D, so total is 60. Now, and other people have done things like this where they have a camera and they have a projector and they move the object and capture the 60. So people have built this race all the way back in 2003 in Xgraph. Okay? Now, again, it will take 4 million pictures if you have to do that. Done on one pixel at a time, one pixel at a time, one pixel at a time, and so on. Right? But now if you switch them, what's the benefit? Because all the cameras can work in parallel. All the projectors could not work in parallel. Only one projector could be on at a time. But all the cameras can take the picture at the same time. Right? So now all I have to do is turn on one pixel of the projector and all the cameras take the snapshot at the same time. So instead of taking 4 million pictures, I can just take 1 million. And I can put as many cameras as I want. And by switching the role of the projector and the camera, I have reduced the total number of samples I have to capture. Total number of time slots I have to. Total number of samples remain the same. Kevin is not happy.
Well, I have a question, but I think it's going to be answered on the next slide if I remember correctly.
All right, so we'll do that. Okay, so it's still 60. So this is how they did it. Instead of creating 16 cameras, they just took one camera, or 16 megapixel, and they just aimed it at these mirrors. So that becomes kind of a virtual camera. And then one projector. And from this, they're going to create an illusion that they have 16 projectors and one camera. So, results, hopefully. So, card experiment. So, do they need a camera for the card experiment?
No.
What do they need?
Light or a color sensitive photo detector.
They just need one photo detector. They could have done it. But for some, they're just showing that for simplicity. Animations. All right. So there are some other experiments that show, how they use that multi-planar mirror thing. Any questions on that, by the way? Yeah.
Maybe I just forgot this, but so if you have a 4D or projector setup, they can actually project where the camera might not be able to see. And then maybe that would reflect onto the ground and then the camera could see it. But if you flip them, then the projector can't illuminate like occluded stuff.
That's the same example in the playing card.
Yeah, it is.
So it still works. So did you understand his question?
Yeah.
When we are writing this whole thing down, we had this implicit assumption that when the projector emits light, the camera can see it. If it doesn't see it, we cannot ignore it. But that's not the case. Even if the camera cannot see it, so the example we have there is you have a card, and let's see how this scenario goes. I'll just go back to that scenario. You have a card here, and you have a projector, it shines light, and then you have a camera, and none of the cameras can directly see this pixel because on the other side of the playing card, but it's going to see the reflection that comes from all these areas here. Okay? So you're still going to see that yellow or red glow on the book from the scan. So remember, you don't have to see, the camera doesn't have to see that pixel directly, that patch directly, to be able to compute how it will look when you switch the camera and projector.
But just as in the example where the horse was uploaded by the emblem, there can be cases where none of the rays actually reach the camera.
That's possible, yeah.
And is it possible to send the ray from the projector in an incident something that will reflect the ray, so it will work?
Yeah, that's fine. I mean, if you put a mirror here.
A mirror is okay, but not a diffusing surface.
No, repeat your question.
Because there is I understand it in one way, but the other way is a bit complex for me. So if you shine light not directly on the card, but on the book, will it still work?
Yeah, then okay, let's take that example. So I have this, I have the card, I have the projector, I just shine the book.
Yeah.
And let's say that thing is still not visible from the camera.
Exactly.
What will I read? I will read the book, I will not read the card.
Yeah. Okay. Well, because there is light that goes on the card as well.
Yeah, let's say that the book has a bluish patch here. The whole scene will lit blue. And I'll say, oh yeah, it must have been the blue spot.
In theory, you might be able to still
read the card.
Yeah, the blue light bounced by the book.
Think of a very diffuse light source lighting up the card, from different spots on the book, effectively, and reflecting back.
It's
on
the third reflection.
Buried somewhere in the matrix.
I was going to ask if there's any clever way you can compute the answer instead of having to take all a million, like you take some pattern.
Exactly. So if you know a priori that certain parts of the scene,
even without any knowledge of the scene,
you can do some probing. I can shine light at one part and see, do I get light from here? I don't. So maybe they are independent of each other. I can shine both of them at the same time. So you can definitely do those probings and quickly figure out how to.
In the paper, they even have the algorithm for it. It's only like this long.
By the way, this will be our next assignment, assignment number 3. dual photography as one of the options. So you can either take 1 million photos, or you can use that short algorithm to reduce the number of samples. But it still takes a long time. You'll have to leave it running overnight, and come back in the morning. All right. So to me, a lot of projects in computational photography are just sheer magic. Being able to see a playing card that you can't even see from a camera. The next one, which I was involved in, is also a lot of fun, or visual chatter. So the concept that, when the two patches are talking to each other, we call it just visual chatter. If they can't see each other, there is no chatter. They can see each other, there is chatter. Okay? And this concept is actually very unique. By the way, when I meet photographers or professional photographers who are kind of technically inclined, and they say, "What do you mean by computational photography?" And I give them all the buzzwords and big definitions, and they don't get it. I try to explain to them dual photography, and they immediately get it. Usually, they say, "Wow, okay, I can't think of, with all the techniques I have in my bag, all the polarization filters and all the flashlights and all the umbrellas and all the fancy lenses, I can't think of a way to create those kind of photos." And the next one you'll see is similar. So giving these concrete examples, at least for me, has been helpful to communicate to photographers what's different here with computational cameras and photography. Okay, so now we're going to look at a little bit more about how light bounces around in the world. Okay, and we're going to think about direct illumination and global illumination, which is unfortunately a wrong terminology, because what we're really talking about is direct reflection and global reflection. But because of some reasons I won't get into, people call it direct and global illumination. Okay? So direct reflection is straightforward. The global reflection is when light bounces around and reaches the location. So the path A is just direct, path B is reflect, reflect, reflect. Okay? So if I shine the spot right here, that's direct. If I look at this shadowed region, that's indirect. Okay. The third one that's interesting is subsurface. Light actually enters the surface, it bounces around, and then it comes out at some point. And marble or skin is a good example of that. This is subsurface scattering. There are some other ones, such as participating medium. So if you have fog or water, then light is going to kind of scatter around and then come and you can look at that. And then finally you have transmissive or translucent. Light is going to transmit through something and then come back to you. Okay. So in this particular case, light actually is coming through this curtain, through the camera. And that's because of diffusion and other types of scattering. Now, what we're going to do is distinguish between direct and everything else. Okay. And I showed this example in the beginning of the class, where you have somebody behind a shower curtain. You can find out what the direct bounce is, and unfortunately it's too dark, but you can probably see the face here, right? And that's the indirect, or because of transmission. This will be one of the options in the third assignment. How does it work? Okay, very simple idea, very very simple idea. You turn on all the pixels of the projector, take a photo. That's easy to capture the direct bounce. Okay. Now, let's introduce a little bit of terminology. Keep it really simple. Okay. Before I go there, let me give you some intuition, and then we'll go here. So imagine if I maybe I'll come on this side. So it'll be more inclined to go this way. So imagine if I have a corner wall, okay, and I take a laser pointer and shine a spot here. What's going to happen because of that is light will again bounce here, right? And that light will again bounce here. Okay? And when I look at the corner of this room, I will see a very bright red spot, but also see a red cast everywhere else. And so the red spot is because of direct, and everything else is because of indirect or global transport. Now, let's say I go from this patch I to the next patch J. Okay, so I'll change the direction of the laser just a little bit. So now I'm going to shine here. Clearly, the bright spot, I'll immediately notice that the bright spot has moved from I to J. What will happen over here? Will I see a change?
Very little, if any.
Very little change. Right? Same here and here. There will be hardly any change. What does it tell you?
It lets you separate direct and global.
We are going to separate direct and global, but this very simple experiment tells you that when the light is bouncing directly, it's a very localized effect. But when the light is bouncing globally, it's a very low frequency effect. And it doesn't really matter whether I shine here or shine there. Okay? So now let's say I wanted to figure out from these two photos, photo when the light is shining at I and light is shining at J, which one is direct and which one is global. How do you do it?
You ignore what doesn't change.
You go for what doesn't change. That's it. Right? The part that did not change is the bounced around part, the global part. And the part that changed is the direct part. That's it. From those two photos, I can tell you which is the direct component and global component. So let's look at it a little bit more precisely. So photo 1 and photo 2. Okay? So photo 1 is direct plus some global. Okay? And the second one is some direct plus some global. Okay? Now, we know that when I change the light a little bit, the global did not change at all. Right? So I'll call this I1 and I2. If I subtract I1 minus I2, what will I get? These two are equal. I'll just get D1 minus D2. Right? And simply from that, I can figure out a photo that's the distinction between D1 and D2. So I have two equations, and right now I have three unknowns. D1, D2, and these two are same. Okay. Now I can take multiple photos. I can take a third photo. I can shine the laser slightly next position, and have D3 plus global, and so on. So I'll have n equations and n plus 1 unknowns. For every equation, I introduce a new direct, and the global remains the same. Of course, once I start shining somewhere else, if I go sufficiently far away from this, the global will change eventually. It will not see the same. But this is a very simple observation. Okay? So going beyond that, let's do some really simple experiment. Instead of what we are interested in is not shining a laser at a time, but I'm going to put a bulb here. Right? I'm going to turn on the flashlight, and I want to know when I take a photo which part is direct and which part is global. So I don't have this choice of doing one pixel or one direction at a time. How would you do that? That's the SIGGRAPH paper.
Maybe I can't answer.
You can't answer it because you're at Columbia.
Yeah.
Okay? And I'll give you a hint. Instead of taking thousands of pictures, we're going to take exactly 2 pictures. Okay? We're going to replace this bulb with a projector. Okay? I'm going to project one pattern, take a picture. I'm going to project a second pattern, take a picture. I1 and I2. The globals will remain the same, and the direct will also be related. And from those 2 pictures, I'll be able to figure out what's direct and what's global.
Make the two directs inverse grids.
Exactly. So, when somebody asks you a question that there are exactly two patterns, there has to be some symmetry or something. Right? So, I'm glad you're catching on that. So, the answer is very simple. Did everybody get it? Or you want to, there is more than one solution, but they all have the same principle, but they are inverse of each other. So, the simplest one would be I'll show a checkerboard pattern, and I'll show the inverse of the checkerboard pattern. So, let's take that a little bit further. And if I shine now, instead of one laser, I'm going to shine multiple lasers, right? Because I'm going to turn on every alternate pixel of the projector. So I'm going to shine this, and shine this, and shine this, and so on. So let's say I turned on all the even pixels of the projector and take a photo. Certain pixels will be bright, the next pixel, certain patches will be bright, the next patch will be dark, bright, dark, bright, dark. Okay? And that's my photo I1. Now, if I project the exact inverse of that, the pixel that was on is off, and the one that is off is on. What will happen to the global? It will remain the same, based on the earlier experiment we saw. So, in the first picture I have some global, in the second picture I have some global. Okay? And in case of direct, I put the direct here, and here I had basically 1 minus direct. Because I just inverted it. Okay. And you can make the problem even simpler. Right? And these are what the equations are, so we'll go through it very quickly. You project the pattern. Look at the pixel. In this case, it's lit. It's receiving the direct component and half of the global component. Because remember, if I turn on all the pixels of the projector, I'll get certain intensity in the dark patch. If I turn on only half of them, then the global intensity will also go down by half. Right? So the alpha here is just half. So what I got in the first one is direct plus half. If I switch the checkerboard, I'm going to again it's D, right? Because it's just inverse of that. 1 minus D is again D because it's just half. And again half of G. That's it. So we have 2 equations and 2 unknowns. The direct component and global component. If I take a subtraction, I will get. What will I get?
Are they exactly the same equation?
Yes. So I need to call it D unit. Although they're related. Right? So all I'm going to do is take these 2 pictures, find the max of the 2, okay, and that's going to be my direct, and find the min of the 2, that's going to be my global. Okay. So if I look at this particular patch, when it was not lit, it received, so think about this patch, okay, particular patch. So I of X, let's call this patch X. This received direct plus half global. But unfortunately, this particular one did not get a direct at all in the first picture. In the second picture, again you have D plus half G. In the second picture, I did get the direct. Okay? So the first equation is half G, second equation is D plus half G. If I just subtract the 2, I get the direct. And then if I do additional manipulation, or if I just take the minimum of this 2, I will get the global. And if I just subtract the 2, I will get the D. That's it. So from just 2 pictures, I can tell you what bounced straight from the wall and what bounced around. This is almost like magic because physicists build really expensive equipment, laser equipment, to solve this problem of what's the direct bounce and what's the global bounce. And now we have come up with a very simple technique where we just change the illumination, which we call computational illumination, to figure out what's direct and what's global. Yes?
So by figuring this out, if you eliminate the global illumination, basically you turn a light bulb into a very high collimation device, like a laser. So you remove all the ambiguity with all the indirect and global
Right.
to a very precise. So it's a way to use a light bulb like a very high collimation.
I don't know what you mean by collimation. Just one spot, you mean?
Yeah, the view of the spot
is very high. Yes. But as you can see, even if you have a very narrow spot, it still has global scattering.
Sure.
So collimation alone does not give you.
Sure.
So the right way to think about this is imagine there's somebody who's sitting in this room, okay, and there's a wall. Okay. Now think about two different pictures. Imagine this wall is white, okay, and I turn on a light source. Okay. What will happen is, and this is what the difference between professional photographers and consumer, right? If you go to a professional photographer, they'll put a nice white drop. I think Masuro, you have that box in your office, right? And the reason the box is white is because you want to see the object nicely lit from multiple directions because of scattering. Okay, you will get one type of picture. Now imagine if this box around the object is completely black. So that light hits this thing, it goes to the reflector, but nothing comes back because it's completely black. The picture that you would get when the rest of the world is completely black would be the direct illumination. There's no scattering going on. As opposed to putting it in a white wall where you would get this.
So it's a bit like being in an anechoic chamber or something.
You can think of it that way. So if you go to an anechoic chamber, you feel really strange. I mean, this wall I can hear my echoes, and that kind of helps me change my tone because I know whether I'm talking too loud and so on. Okay. But sometimes when you're at a performance, you go on the stage and you can't hear yourself. Right? That's a similar feeling. So if you eliminate all the other bounces, that's the direct component. And so as you can imagine, in photography, the global component is very critical. It's very, very critical. When you're shooting a movie, and even if it's a nighttime scene, the director will always put some small light sources here and there, so something is still visible on the screen, and you can figure out what the characters are saying. If a real nighttime scene doesn't look like that, but by creating this global illumination, they just create enough brightness so that you can discern. So it's extremely powerful to figure out direct versus global. Now let's see how we can use it. Okay. So before we see that, let's look at some real world objects and how, for them, direct and global components really matter. Okay. So we have marble, we have this very diffuse candle wax, water with some glass with some milky water, and interreflections between the walls, and so on. Okay, and this one, if you do this trick, you'll see something really interesting. What will you see, let's say, at the corner here? By the way, do you know why the corner of any room looks really, really bright? It's all interreflections. Okay? There's more light reflecting back and forth there than anywhere else. That's why it looks bright. What about this wax here? Most of the light is actually scattering inside, so it's almost all global. Yeah. Right? Same with marble and so on. So we'll see how it looks. I don't have a movie, but this is how the world looks. This is all the light that's coming straight back. If you look at wax or milky water, none of the light actually comes straight back. It all bounces around before it comes back. Okay. On the other hand, over here you can see that light is actually reflecting, and also in the corner you can see that everything is because of interreflection. There is a bug here. Because in the corner you see it's very bright. It shouldn't be, because the corner here should not be any bright than the rest of the wall, because it's just a direct reflection. But there's a bug. There's a limitation to this algorithm in terms of its resolution.
Well,
that's why it doesn't capture.
So you get miscategorized because your checkerboard size isn't small enough.
Exactly. Your pixels are not small enough to capture that color.
Another question is, so in the previous example with the shower curtain, the direct component lets you see through the scattering curtain?
No, the global component.
The global component. Okay, never mind.
So
Yes.
it's a good technique also to take picture of an aquarium. Because,
Aquarium?
yes.
Yeah, certainly.
So then,
Yes.
Is there a redefine these like to adjust how much global you have or direct you have in there?
Beautiful, right? So you can play these tricks in your Photoshop, where you don't just changing the brightness, but you're changing the global versus direct. So all the wax will start glowing, but the regular diffuse surfaces will not. You can play all those tricks. Also with skin. It turns out, we'll see later, that if you lived in a world where direct and global could be separated, there'll be no racism.
So you go back. How about the highlight on the glass on the direct side?
This one here?
No,
This one? Yeah. So you will see later that this technique doesn't work for highlights.
Okay.
And I wanted to think about why that is the case. Right? So let's look at some fun examples. So this is a V groove in a wall, right? Which we already saw. It should look flat, and only in the corner you'll see internal reflections. Here's a failure case. Okay. If you have a shiny mirror, then if I shine a laser at the mirror, I'll get. So let me draw it properly. If I have a mirror and I have a wall, if I shine the laser here, it reflects here. Right? On the other hand, if I have a wall, then if I shine a laser here, it reflects everywhere. So it only reflects in one spot. If I change the laser direction to slightly here, it goes in a different spot. And the global effect of here versus here is quite different. As opposed to here, if I shine this spot versus this spot, this will have the same reddish glow, same reddish cast. But that's not true for specular objects. That's what the technique is.
But, would you even call that global illumination?
So global illumination is anything that has more than one bounce. So by the definition of global reflection, anything that has more than one bounce of the photon is global. So yeah, it fails. Depending on your application, you can say, hey, specular is not part of my world, and you can get rid of that. So it has these issues. So now we have some interesting examples. I really like this part. So interreflection, eggs. What should you see? Because between those eggs, there's going to be a lot of light bouncing around.
Yeah.
So it'll all glow up. It's at the bottom right. You can also do a trick where you can do it in sunlight. You can just do the inverse effect. I can just take a stick and move it. And remember, if I take lots of images, the minimum of all the images is the global, and the maximum of all the images is direct plus global. That's it. Those two equations are all done. It's very easy. So if I move a stick and shoot a video, at any given pixel, I look at all the frames, and the minimum of that is the global component. Right? So you can do this outdoors. Again, I don't have a video. Sorry. So in the shower curtain, our favorite example. Same effect. And here, light that bounces straight from the curtain is the direct component. Any light that actually bounced around and came back to the camera is the global component. So anything that's behind the curtain will actually play a bigger role in the globe. Now the problem is that even the texture on the curtain actually has some subsurface scattering. It has some thickness, light is bouncing around and then coming out. So that's kept here as well. But you can capture it. Yes?
What was the mesh diffuser that you were using?
So yeah, that's a good point. So there are multiple ways you can do it, right? I can either use a projector, or I can just take a mesh. I can just buy the Home Depot, buy high frequency mesh, put a light source, and just move the mesh in front of it, and shoot a video. So to create this light projector that projects a checkerboard and its inverse, I don't have to use a projector. I can use the light source and a mesh, or a stick, whatever it is.
So for those you actually need video, for the stick you need video, or do you need to just what you need for a whole bunch of, not only just two pictures, which are
You're taking more pictures.
Okay.
But the minimum number of pictures you need is 2. Because you have 2 unknowns, direct and global. And then this is your fish tank, where you want to see very clearly in murky water. That's direct. Actually, it turns out most of the light is bouncing around and coming at you. And the picture on the left, maybe I should play with the lights here.
Looks like there's a color shift.
Yes.
Is that better?
No.
I don't want to discuss this. Too dark.
Yeah, there is.
And this looks like some kind of a computer graphics rendering. Why is that?
Because in the old days they didn't have global.
Exactly. Because cheap computer graphics rendering is basically just direct bounce of light. It doesn't think about, RenderMan and Maya doing all this bouncing of light around and so on. So, when Pixar decided to make animation movies, which movie did they make first? Toy Story. Why? It's all plastic. It's very easy to render. They cannot do ants, and they cannot do fur, and they cannot do rain, and they cannot do fog. It's just toys. Toys are the easiest thing to render because they have very simple surfaces. And they all look like this on the left. So we can
So what explains the color shift that's in there?
Because if you know how light reflects inside some kind of a scattering medium, then it has a preference over certain wavelengths. If you're underwater, then red is suppressed and blue-green is not. Right? So similar thing here. So it always has a blue-green tinge because what you're scattering suppresses one wavelength but not the other.
Well, so the scattering goes like omega to the fourth.
Mm-hmm.
So the blue should be scattered more.
So yeah, you in the global component you see more bluish,
Okay.
right? And the bluish tinge on the red cup there is gone on the left.
Oh, okay, I see.
Because this is just a direct bounce. We're ignoring the scattering. So imagine the projected pixel comes, it scatters through the water and then hits the red cup. And I'm just trying to measure that. I don't want to worry about how everything else is contributing back to that red cup.
In all the example you showed, you either use a light bulb or a projector.
Mm-hmm.
Could you use the light of the sun?
So the example of the stick was with the sun.
Okay, but can you modulate it? Could you apply a...
Yeah, you can again take a grid or a mesh and just move it and shoot the video. It's the same thing.
But then just out of curiosity, with this whole scattering colors that I didn't get, what's the actual real color of the green cup? Is it?
It's that. If I take it out and put it in free space. No, it's that color.
Green. Okay. So it's the one that
Is it green? I don't know.
Okay.
And then you can play with adding more tinge and so on. As we were saying, like you can have more global component or less global component and so on. Okay. Now here are some really fun examples. You can even figure out what is real and what is fake. Okay, 'cause one fruit is real and one fruit is fake. Let's see. Let's start with the banana. Which one is real? Which one is fake? Top is real. How many think top is real? The bottom is real? Okay, everything bottom is real. What about the apple? Left is real? Okay, right is real? Okay, so for bottom and right and the lemons, left is real? Right is real? Alright. Remember your choices. Okay. Pretty good. So, but how would a camera do it? Right? If I just take this picture and give it to a camera, like a computer vision algorithm, it's almost impossible to figure out which one is real, which one is fake. And the reason for that is when you make a plastic or a fake fruit, you only try to match its outer appearance. You don't try to match its inner appearance. Right? So in case of the apple, you realize that light bounces around inside in a real apple and it becomes reddish. That's what gives the reddish color. But in a fake apple, no light bounces around. So you know which one is Apple and which one is Microsoft. Over here, it's a little bit more complicated because although it's fake, it has, first of all, the direct bounce from a real banana is actually very different color. Right? And this is all because of the ripening that's happening inside. And when it comes to lemon, this one is really complicated for me because in a real lemon, if you look at the direct component, this lemon is maybe it's a good quality fake because even the internal reflections inside that fake lemon, and I think I've seen those fake lemons. They are a little bit kind of soft and fuzzy, so light can bounce around inside, as opposed to apples which are just hard. The way to figure that out is if you look at the direct component of a real lemon. First of all, you realize that it's green. It's not blue. It's not yellow. And the real lemon actually has a texture that you never see directly. But when you see the real direct bounce, you see that reflection. So a lot of interesting things here. I wish I had it in my cell phone camera so I can figure out. So this is, by the way, a great trick to figure out if something is ripe or not. If it's more ripe, light will bounce around more inside because its permeability is different. So I can build a cell phone camera that can tell you if a fruit is ripe or not.
And it's also like in photospectrometry, you can see the blends is out or not, its colors, combine.
Exactly.
You know lots of things.
Yeah, you can do it with that as well. But this is another kind of tool you have,
so
which can be implemented very easily.
If you 3D, if you do the face of somebody, you should actually put everything inside. Because of this as well, there is internal reflection in the head as well.
I'm sorry, repeat the question.
You show that it's a way to distinguish maybe something alive and something that is not fake from the real.
So whether there's a makeup or not.
For example.
Yes. So unfortunately, this trick will also tell you if somebody is wearing makeup or not. Okay. Let me just talk about ethnicity. So as you know that hands of different ethnicities look very different, but skin. But if you look at the direct and global, the direct is almost always gray, and all the pigment is in the global. So if you take people of different ethnicities, I hope I have the example, the direct component is almost the same.
Are these normalized at all?
They may be normalized, yeah. But the global component is what actually gives the real color.
Okay. So when you add.
So there is no color. The direct reflection has no color. So if an alien comes in and can see only in direct illumination, that's how to look.
You should also look on Flickr for infrared photographs.
Yeah.
They show people are really wrinkly.
Exactly, yeah. And we'll see some thermal IR pixels, and that's also. Anyway, I'll go through it quickly.
What happens if you do this with IR?
I mean, it's the same effect. Sometimes light, at some wavelengths, there's more interreflections than others. So you can imagine some surfaces are actually darker in a particular wavelength. So the situation I explained, where you have a person in a white room versus a black room, their appearance looks very different, right? Because there's direct plus global in the white room, but not in the dark room. So at a particular wavelength, the room may be black, and you'll see just direct. All right. So let's take a break, and then we'll come back and talk about optics and light force.